In linear algebra, an important concept is what is known as linear combinations. So what's a linear combination, and what does it mean for something to be a linear combination of elements or vectors? So let me give you a definition. If I have v1, v2, vn. So if I have a sequence, or not necessarily a specific order, but if I have a certain number of vectors, v1 to vn, so these are vectors, hence the arrows here. If I have a certain number of vectors, so if v1 through vn are vectors, okay, and then I've given a certain number n of scalars, so and c1, c2, c3, cn are scalars, meaning that each of these belong to R, belong to the real numbers. Then a vector, let's call it vector u, written as c1 times v1 plus c2 times v2 plus, I think I know where you're going with, where I'm going with this, c3 times v3 plus ... until cn, until the very last vector and scalar, first vector for scalar. So multiplying each vector by a certain scalar and representing this by a vector u, we can say that u is a linear combination of the vectors v1, v2 through vn, through and until vn. So that's what it means for something to be a linear combination of a set of vectors. You have a number of scalars, you have c1, c2, c3 until cn, and you're multiplying, you're given a multiple of each vector v1, v2, v3 through vn, and you're representing this by a vector u by adding these vectors, all of them together, and making them equal to a vector u. So you say that u is a linear combination of v1 through vn. Now a problem that usually comes up in linear algebra when you're dealing with linear combinations is they usually ask you to show that something is a linear combination. Something is a linear combination of let's say, of a list of vectors. So vectors here is a very loose term. It can be any kind of element. So any element, right? It can be, you can say that matrices are a matrix can be a linear combination of different matrices, or polynomials can be a linear combination of different polynomials. So vectors here is just a very broad, very general term for any element. So it can be a matrix, polynomial, it can be a vector, so an actual vector, and etc. Any kind of object or element. So showing that something is a linear combination of a list of vectors, it isn't very tricky, but you just need to know the method to it. So I'll give you an example. I want to know if is 2, 6, 8, the vector 2, 6, 8, a linear combination of the vectors 1, 2, 1, 0, 2, 3, and 2, 0, minus 3. So in other words, what I'm asking is, I'm asking if it's possible to represent 2, 6, 8. 2, 6, 8 by C1, any scalar C1 times 1, 2, 1 plus C2 times 0, 2, 3 plus C3 times 2, 0, minus 3. So in effect, what I'm asking for in this question is, can I find scalars C1, C2, and C3 such that these three things added together will give me a vector 2, 6, 2, 6, 8. So the easiest way to do this is to put this in to create a system of linear equations and to put it into a matrix. So let's create a system of linear equations. So I'll start with 2 is equal to C1 times 1 plus C2 times 0 plus C3 times 2. So 2 is equal to C1 plus 0 times C2 is just 0 plus 2 C3. Then I'll have 2 C3, and then I'll have, in my second row, I'll have 6 is equal to 2 C1 plus 2 C2 plus C3 times 0 is 0, so I'll have plus 0. And then I'll have 8 is equal to C1 plus 3 C2 minus 3 C3. Okay, so I have my system of linear equations, and I want to solve for C1, C2, C3. So I just need to put this in a matrix. So let's see. I'll have C1, C2, C3 here, and then my constants over here. So I'll have 1, 0, 2 is equal to 2, then 2, 2, 0, 6, and then 1, 3, minus 3. So now I just read off my coefficients. So these are just my coefficients, right? Okay, so now let's just do some row reduction. So we'll start with this guy, and we'll do R2 minus 2R1, and R3 minus R1. So row 2 minus 2 row 1, and row 3 minus row 1. So what we'll get is, so let's keep this here, and we'll get 0, 2, minus 4, and then 2, and then we'll get 0, 3, minus 3, minus 2 is minus 5, and then 6. Okay, and now what I'm going to do is I'm going to divide my second row by 2. So I'll do R2 divided by 2. R2 divided by 2. So what that gives me is 0, 1, minus 2, 1, 0, and then the rest is just the same. I'll just recopy it. 1, 0, 2, 2. Okay. So now I'll start with this guy. There's nothing here. So now I'm just doing Gauss-Jordan elimination. There's nothing here. So I'll check here if I need to row reduce, and I do. So I'll do R3 is equal to R3 minus 3 R2. And that'll give me, so this is the same, it doesn't change. Then this also stays the same, the second row. So I'll get 0, 3 minus 3, 0, minus 5, minus 3 times minus 2, 6, so minus 5 plus 6 is 1, and that's 6 minus 3 is 3. Okay, so now I'm here and I want to row reduce these two guys, right? So I'll do R2 is R2 plus 2R3, and then R1 is R1 minus R2 R3. Sorry about that. 2R3. Okay. So what I'll get this stays the same. And this is 1, 0, 2. So 1 plus 2 times 3 is 6. So this is 7. This is 1, 0. And then 2 minus 2 is 0. Then 2 minus 6 is minus, whoops, sorry about that, guys. And then this is minus 4. Okay, so my result is I get C1 is equal to minus 4, C2 is equal to 7, and C3 is equal to 3. So your automatic reflex is to say yes, because I got a solution. So I got a solution, so that means that I can express this vector by a linear combination of these three vectors using C1 as minus 4, C2 as 7, and C3 as 3. So yes, that's true, but it's always a good thing to do to check to see if your answer was actually right. So what I mean by that is I want to see if this addition is actually if this sort of linear combination actually gives 2, 6, 8. So let's see. I'll just replace it here. Minus 4, 7, 3. So this is minus 4, 7, 3. So if I do minus 4 times 1, it's minus 4. Plus 7 times 0 is 0. Plus 3 times 2 is 6. So I'll get minus 4 plus 6, which is 2. So that one's good. Then the second one is minus 4 times 2. So that's minus 8. So minus 8 plus 7 times 2, which is 14. So plus 14 plus 0, which is 6. So that's also good. And then the last one is minus 4. So minus 4 times 1 plus 21 minus 9. So that'll give me minus 13 plus 21. So that's 8. So it's good. So that means that the solution I got here was right, and that means I can write my vector 2, 6, 8 as a linear combination of the vectors 1, 2, 1, 0, 2, 3, and 2, 0, minus 3, because I can get a solution. I can get a solution for C1, C2, C3, where once I multiply the vectors out, then I'll get the resulting vector that I need. In other words, 2, 6, 8. So that's how you check if something is a linear combination of, well, that's how you check if vectors are linear combinations of one or more vectors.